Okay, we're going to talk about missing data today, and I'm going to look at this R script with us today. Missdatascript.r has some simulations in it. Let's go to the script first. So missdatascript.r. Right. So we're going to be talking about what to do with missing data. Often when you have a data set, there will be one or more missing values. There's a pretty substantial kind of subfield of statistical research that deals with what to do with missing data. There are folks who have made their whole careers out of missing data stuff. And it is fairly technical. The statistical issues that arise and some of the methods that are proposed to deal with missing data, some of them are pretty technical. So it's a little bit challenging to know what to do with missing data in every circumstance. The problem is that it can have kind of a big impact on your methods if you don't take care of it appropriately. I mentioned last time that the main consideration when we're working with missing data and deciding what to do about it is what mechanism do we think gave rise to the missing data. So I mentioned last time there's different mechanisms that have been defined. There's one called missing completely at random, or MCAR, MCAR. That is the easiest to deal with. That is the case when the probability that a value goes missing has nothing to do with the value that it would have been, or any other value in the data. So it's a completely random event that a value went missing. Somebody just forgot to write down the number in the data set for this individual, or the value was corrupted somehow, just by random features of the computer storage system or something like that. So there's on the easiest end, there's this missing completely at random. On the hardest end, there is what's called missing not at random. Let me go ahead and go to our slides again real quick and remind us about this. So these are the different mechanisms that we'll consider. The first, third, and fourth are the most widely cited and referred to. The second one is kind of a nuanced case. But missing completely at random would mean that the probability an observation, an attempted observation, is missing. Here I'm saying RIT equal to 1, where RIT is an indicator for whether observation I, t, the attempted observation for individual I at time t, is missing. Missing completely at random says that the probability that this observation is missing, given all the data, response and covariates, this would be the complete data, so every observation. Given that, MCAR means that the probability of missingness just equals a marginal probability, and in particular does not depend on any of the response values or any of the covariates. That if MCAR is what's driving missing data in our data set, then every individual and every attempted observation in our data set has the same probability of being missing. It's not that the sicker patients are more likely to be missing. It's not that the older people are more likely to be missing or anything like that. Completely random. Missing not at random is the other extreme. the hardest case to deal with. And this one says that there is no simplification to this probability. The probability of an individual missing depends on the observations of other people in the data set potentially, and potentially on the value for this individual that we would have seen. As opposed to missing at random, the third entry here, which says that the probability of missing, given all the data and the covariates, is only dependent on the data that we actually observed. So if the probability of missingness depends on data that we observed, then we can hope to estimate that probability and move on from there. But when the missingness depends on the value we would have seen for an individual, like suppose this is a clinical trial and the response variable is maybe pain, some measure of pain. If you are more likely to drop out of the study or miss an appointment when you're in higher pain, then the probability of missingness depends on what the value of that pain measurement would have been. So suppose somebody in our clinical trial is very sick, nauseous, and uncomfortable, so they don't come into the study center for their evaluation. We won't know what their pain was then because they didn't come in. We don't measure it. It's missing data. So the missing not at random mechanism would apply in that scenario. If the value of the variable that we are trying to measure is a part of the missingness probability, then it's called missing not at random. So let me also say something briefly about the kinds of things that people do with missing data. Suppose we have a data set, N by P matrix of numbers and categorical variables maybe, and there are a few cells scattered throughout the matrix that are missing, NA. One possibility for proceeding would be to drop all the individuals who have any missing values and only work with the complete cases. If we get rid of every individual with any missing values, then there's no issues computationally anymore. You can compute averages and standard deviations and everything without a problem. The problem with doing that is that you're getting rid of a lot of information, potentially. If you have 20% of your individuals have at least one missing value, then you just lost 20% of your data. That's not ideal. Another thing that you'll see people do with missing data is so-called imputation, which means if this particular individual has a missing age, say, suppose we went and got the average age of everybody who we had data for and plugged that in. So imputation is trying to fill in the missing values with some reasonable proxy or derived number. When it comes to imputation, there's a couple of different flavors that we'll talk about. There's what's called single imputation, and then there's a more sophisticated method called multiple imputation. Multiple imputation is about as sophisticated as we're going to get when it comes with dealing with missing data. If our data are missing at random, it turns out imputation, and in particular multiple imputation, is a sensible thing to do. And it enables us to have valid statistical inference, even with missing data. What R does is essentially treat the missingness like missing completely at random. By default, if you try to fit a linear regression model or a Cox model to data that has some missing values, R is going to do the best it can to estimate all the coefficients and all the parameters using just the complete observations. And in doing so, it is making an assumption that the missingness is not missing not at random, or informative missingness is another way of saying that. Okay, so before we go further in the notes, let's just look at some examples of what missingness does. I'm going to simulate first in the script a univariate sample. So we're just going to be interested in estimating a mean. We have data from some population with a mean and a standard deviation. Let's try to do inference on the mean when some proportion of the data is missing. To get us started, we're going to work with missing completely at random. So let me show you what missing completely at random looks like. Let's consider a sample size of 50. We're going to simulate 1,000 times. The population mean is 5 and the standard deviation is 1.5. And the proportion of individuals, or proportion of observations that are missing is going to be 0.3. 30% of all the cells in the data matrix are going to be allowed to be missing. Okay, so what I'm doing here is simulating data for all the simulations. I want a sample of size 50, but I want to simulate 1,000 samples. Capital Y here is going to be a 50 by 1,000 matrix. Give me 50,000 draws from a normal distribution with the chosen mean and chosen standard deviation from above. Then create a missing indicator, like that capital R from the notes. Create a missing indicator by essentially flipping a coin that comes up heads with probability 0.3. Give me R binom, that's random draw from the binomial distribution, 50,000 times. Each time, one draw, or one trial. And the probability of that trial being, quote, success, or in other words, this individual being missing, is pi, 0.3 currently. Miss is going to be 50,000 zeros or ones. Here, let me run all of this through here. So we have Y 50 by 1,000, and miss is a vector 50,000. So if I table miss, roughly 30% of the attempted observations are going to be missing. So now I'm going to create the version of our data that has the missing values in it. Y miss, set it equal to Y initially, and then wherever miss equals 1, put NA. Miss is a vector, Y is a matrix, but if you provide, so Y has 50,000 elements in it, it's 50 rows, 1,000 columns. If you provide a 50,000 vector, what it's going to do is apply column by column. It's going to fill, or it's going to take the first 50 draws, first 50 values of miss, and apply that to the first column of capital Y, and then the next 50 are applied to the next column, and so on and so on. So this command here, Y miss, where miss double equal 1, is going to pick the corresponding cells throughout the whole matrix of capital Y. So let me show you what it looks like after doing this. Y miss is 50 by 1,000. And let's look at the first 50 rows and first 10 columns, say. So we started with there were numbers everywhere, and now there are these NAs scattered around in our simulated data. Each column is, again, a simulated data set that we're going to play with. So we might have a sample of size 50, like this in column 1. We have numbers, but in some cases we have NAs. We're interested in doing inference on the mean, the population mean. If we didn't have missing values, we know what to do. Compute a sample mean as an estimate. You could do a t-test, a one-sample t-test. You could do a t-based confidence interval as well. But now that we have missing values, what are we to do? So here's what I'm going to do. We're going to compute an estimate of the mean and an estimate of the standard deviation of the mean estimate, so the standard error of the sample mean, according to 3 different approaches. The first is we're going to use the complete data. So capital Y we simulated is all the data. There's no missingness in there. The missing data are in Y underscore miss. So what we could do is cheat, since we're playing a simulation game, and estimate the mean and the standard deviation of the mean using the complete data. That'll be like our gold standard to compare to. The second technique will be to only use the actual observed data in our calculations. We have a sample of size 50. That's 50 attempted measurements. But what we could do is just filter out any of the observations that were NA, and that leaves us with 30 observations or 35 observations, whatever. We could use those complete observations, the subset for which we actually had a number, to compute mu hat and the standard deviation hat. And then the third way I'm going to do this is to replace the missing values with some sample statistic. If I want to do inference on my 50 attempted measurements and there are some missing values, one thing you might try to do is replace the missing values with the average of the complete values. So we could take all of our NAs and our 50 observations and replace them with, say, the average of the numbers that we actually saw. That's an example of what's called single imputation, which is not generally a good strategy. So we'll see how we do here. But later I'll introduce multiple imputation, which is better. All right, so I'm going to set this up. We're going to keep track of estimated mu and estimated standard error of mu hat by these 3 methods. First is analysis with just the complete data. So we're going to cheat and use the original data that before we had put in the missing values. Mu hat, that's just a sample mean. So this is computing, I could compute this more with simpler syntax. Why don't we do call means? It's the same thing as this code here. Just compute y bar for all the simulated data sets. There's no missing values. If there were missing values, we would get NAs from this calculation, because if you ask R to compute an average when there's a NA, like the mean of 3, 0, NA 5, it will give you back NA. But capital Y, there's no NAs. So just compute the column means. I must have written this a long time ago because this is could be simpler, could be written more simply. But all I'm doing now is computing the estimated standard deviation of the sample mean. So that would be an average square deviation between the data and the sample mean. This also could be done with different code that's easier to read. If I said SE hat complete is, let's do apply to Y, column by column, SD, and then divide that by N. So the standard error of a sample mean, the variance of a sample mean is sigma squared over the sample size. The standard error, or it's just the standard deviation, would be the square root of that. So here I'm computing square root of the sample standard deviations of each of the columns divided by the sample size. This is like S over the square root of N. But I'm using call means and apply because we have 1,000 columns representing 1,000 simulations. So I'm going to comment this out. We don't need this code anymore because the above does it as well. So let's get these computed here. Mu hat has 3 rows and 1,000 columns. We are computing sample means for each of the 1,000 simulations. Here's the first 10 columns of what we have currently. My complete data estimates of the mean are just Y bars, sample means. And similarly, we have complete data estimates of the standard error of the sample mean. There's the first 10 columns. And how about we assess coverage probabilities of 95% confidence intervals? We've done this a few times with our simulations. If you want to consider a statistical method and how well it works as an inferential method, one way to assess it is to simulate, apply it, and ask what proportion of a 95% confidence interval contains the truth. If the method is a valid method, then approximately 95% of the confidence intervals should contain the truth. Let's keep track of how many of ours. With our above mu hat and SE hats, let's do a normal based 95% confidence interval. Estimate plus or minus 1.96 times the SE of the estimate is what this is doing. And this has computed, let's see, a single proportion of coverage. We had 1,000 simulations. For each simulation, we estimated the mean, estimated the standard deviation, put them together in a 95% confidence interval, and then we asked what proportion of those 1,000 intervals contained the true mean. The true mean that we're simulating from, equal to 5. We got 88% which seems kind of low. I'm going to rerun this and see if it changes much. $88 again. So we're asking lower bound less than or equal to mu and upper bound greater than or equal to mu. Let's see how it goes with the other ones. That should be 95%. It could just be sampling variability that's causing it to be a little low, just by chance, I'm not sure. But it should be 95% because we haven't done anything. There's nothing unusual about these data that we just played with. No missing data, and we did a reasonable confidence interval calculation. What follows is, what if we only consider the complete observations? So to estimate a sample mean, one thing we could do is remove any missing values and just compute the average with the complete data. In order to compute the standard deviation, we could just remove the missing values and compute it with the complete observations. So I'm going to keep this code. It's kind of ugly looking, but what it's doing is what I just described. So do sample average and standard deviation calculations, but only use the values that are not NA. What I'm doing here is computing for each column how many observations do we actually have. We have 50 attempted observations for every single simulation. This is computing how many of them were not NA. This is replacing all the Y values that are NA temporarily with a 0, so that when I compute an average, all the missing values don't break the calculation. They're just zeros. So when I do like matrix manipulation to compute an average, the zeros will be used in the calculation. If they were still NAs, they would break the calculation. So zeros allow this to be done, and then I divide by the correct number in CO, because we computed that above. That's the number of actual observations. So we're not counting those zeros in the calculations. And then what follows is computing the standard error of the sample mean. Again, just using the complete observations. Then down here we'll ask, like we did above, what proportion of our 1,000 95% confidence intervals contained the truth. And here it's 94%. So this should be right at 95. The one from above should be right at 95. This one should also be right at 95 because of the way that the missingness happened. Missingness in this simulation is completely at random because we chose who was to be missing just essentially by flipping a coin. There's no reference to what the response value would have been for the missing value or for any of the other ones. Missingness was completely a random assignment. So working with the complete data versus working with just by just throwing out the missing data should not have a systematic difference. There's not a difference. It's okay to just work with complete data if any missingness happened completely at random. The last example here is let's replace the NAs with some number that we compute from the observed data. So that's what I'm doing here. I'm looping through the columns, and whoever has a missing value, they are being replaced with that sample average that we just computed in the previous step. In the previous step, we computed the average of just the complete data. So now, instead of proceeding with only the complete data, we're going to replace the missing values with that average that we computed. Everything else is comparable to the above. Compute a sample average, compute the standard error after replacing any missing values with some imputed value. So there is no missingness anymore as we're working with these data. And here's the calculation of coverage probability, 0.81. So after imputation, the coverage probability dropped below the other two, and that's a general result. The issue with doing imputation like we just did is that we have used the data to estimate something that we then used with the data and moved on. So we have to keep track of what parameters have we estimated. The more parameters you estimate, the more degrees of freedom you've used up in your data. By imputing, we computed an average of the complete data and plugged that in. We're going to be moving in the direction of overfitting our data. This 0.81 is substantially lower than it should be, and that's because of overfitting like behavior. Let me make this picture. This picture is a comparison of the estimated means and estimated standard errors. So left panel shows the estimated means. The leftmost box, for example, is by using just the complete data. This was before we created any missingness. The estimate of the sample mean across all 5,000 simulations, it's centered at 5, which is the truth. That's the population mean. And then it has this symmetric distribution about it. The other two, after ignoring missing values or imputing missing values, both of them are centered essentially at the right place. There's no bias in them. But both of them are a little bit more variable than the complete case. Then standard error estimates. For the complete case, the gold standard, when there were no missing values, this is what we got as the distribution of standard error estimates. These are like S over the square root of n values for all 5,000 simulations. The imputed results have standard errors that are pretty similar to the complete case. The ignore case have standard errors that are substantially bigger. Why would that be? A standard error of a mean estimate. So if we, like in our case, we're just saying we have a sample of size 50, IID from some distribution with mean mu and variance sigma squared. So our usual estimate of mu hat, is a sample mean, and our usual estimate of sigma squared is a sample variance, call it S squared. Then the standard error of x bar, our estimated SD of x bar, is S over the square root of n. So if we consider the case where there were no missing values, we had 50 observed numbers, and compare that to the case where we threw out some subset of observations that were missing. In the case with missing, the number of observations that are left, let's call it N0, is less than the original attempted number of observations. So that means our estimate of S divided by square root of N0, that's dividing by a number that's smaller than it would have otherwise been, which means this is going to be bigger than the complete case. We look at this picture on the right panel, the standard error estimate after ignoring the incomplete data is inflated. And the main reason for that is because we simply have less observations. We are dividing by a smaller number in our denominator of the standard error. Here is a comparison of the coverage probabilities. We've already looked at this, but I'll make the picture since I already have the code for it. It's not a very useful picture. So I expect both complete and ignore to be close to 0.95. Complete is a little further away than I expect. But definitely the imputation result is low. 95% confidence intervals is what we tried to compute. 95% of them should contain the truth if they were correctly constructed. For the imputation case, because we have double dipped in the data, so to speak, we used the data to estimate something and then we moved on and estimated other things. That results in anti-conservative inference. Our confidence intervals are actually at lower confidence or coverage probabilities than we would claim. Single imputation is not generally a good idea. Let me show a different simulation while we're on the topic, but now a different mechanism for the missingness. Whereas above, we generated missing observations by a completely random mechanism, flip a coin, and wherever it comes up heads, that's who gets missing. Now we're going to consider not missing at random, missingness. This is the worst case. So again, sample size of 50, 1,000 simulations, mu is 5, sigma is 1.5. Proportion of censored observations will again be 0.3. But now what I'm going to do to create the missingness is so I'm going to, in the second line of that highlighted chunk, I'm going to order or sort the values of the response, and I'm going to take the top so many and replace them with NA. Instead of just completely picking randomly from the 50 observations in each simulation to create missingness, we're going to order the 50 observations within each simulation, and the top values will be censored, missing. So this is like mimicking the scenario that I mentioned at the beginning. Suppose the sickest people are those who you don't have data for. Suppose Y is some measure of a health outcome like pain or something like that. That the bigger number it is, the worse off you are. We're going to simulate the case where the people with the highest values are the ones that get missing values. So the fact that something is missing is now informative in a sense, because you know that people who are missing tended to have higher values. Let's run all of this and then take a look at a couple of pictures. Same code as above. And then here are here's the picture that we made at the beginning. Comparison of means and comparison of standard errors after 3 different approaches. So complete case is the gold standard. This is where there was no missing values. So there were no missing data in the complete case. And we have the mean estimated correctly. We have the standard error of the mean estimated correctly. This is 1.5 divided by the square root of 50 is right around there. For the other 2 cases, ignoring and imputing, there are suboptimal results. In particular, the average, so I think I said it backwards from back here. Instead of taking the top so many and making them missing, I'm taking the lower so many and making them missing. So it's the other way around of the way I described it. These would be the people who would have had the lowest values of our response tend to be missing. And what that translated to in terms of estimates of the mean is overestimates. So imagine you have 50 numbers and you take the lowest 30% of them and mask them or remove them from the data. Then if you use what's left to estimate the mean, you're going to overestimate the mean because preferentially the lower values have been dropped. We are overestimating the mean. In the ignore case, if we just use the 70% of the observations that we're not missing, those are going to tend to be the bigger values, the biggest values. So systematically, we're overestimating the sample mean in this case. And similarly, if we decide to use the complete data to impute the missing values, we would go to the 70% of our observations in the sample and compute an average of those and plug those in for the NAs. But the problem there is, again, the average of the observed observations will tend to be the higher values. So we're going to be replacing missing values with a new number, but that number we're going to plug in is going to tend to be bigger than the average. So here again, we overestimate the mean. The standard error estimates are both off in the ignore and impute cases. Let me come back here for just a second and say something else rather pessimistic about missing data. This missing not at random case, which is what we just looked at, let me complete the story here first and then I'll come back. Let's look at coverage probabilities. In this missing not at random case, suppose we work with just the complete data, or suppose we impute the missing data using the complete data. Whereas our confidence interval should be covering at 0.95 coverage probability, both of these strategies fail miserably in this example. So we only have 30% missing. That's not that bad. But with 30% missing, if you were to just ask R to compute a confidence interval, compute the average and do plus or minus 1.96 times the standard deviation divided by the square root of the sample size, R would, even with the NAs, well, if you use the right flag in the function, it would just do calculations with the complete observations. It would essentially do ignoring. And this would be an illustration of a case where it would be dead wrong. You would not want to just trust R to do whatever it wants with your missing values. And imputing is just as bad. So the mechanism by which missing values come in is critical. If it's of one flavor, you really don't have a problem. You can just ignore the missing data and proceed, and the only penalty you really have is that you've lost some of your data. But if it's of this more sinister style, missing not at random, it can completely invalidate your inference. And so now let's come back to this slide and think about this for a second. You have a data set with some missing values in it. You know that the mechanism by which the data are missing is important to how you proceed, what kind of inference you can do, how you should compute your estimates and all that. So how would you decide in practice which of these missingness mechanisms apply? How can you possibly, for example, know or figure out from the data whether or not missing values are missing in such a way that it's informative? How can you possibly know whether a missing value is missing because the value you would have observed was extreme, say? The short answer is that you can't tell that just by looking at the data. There's really no way to know which of these mechanisms applies. So what I think a sensible strategy is to think more about the study design, to talk with the people who collected the actual data, and ask them to help you understand what would have created. How does an individual have an NA in this data set? What happened? And be looking for ways to say, okay, I don't believe, therefore, that it's missing not at random. If you can at least argue that missing at random is the missingness mechanism, missing completely at random is best because it gives you the most options, it's easiest to deal with. But missing at random is also at least somewhat reasonable to deal with. So if you can at least argue it's not missing not at random, then you're arguably okay and you can handle it. It's when there's missing not at random that there's very little you can do with your data. There are some techniques out there that try to address and enable valid statistical inference even with MNAR, but they're pretty complicated in many cases, unless you have specialized software. There are specialized software packages out there that are specifically for missing data, and I'll show you at least one of them later, but they typically are standalone proprietary software packages that may cost hundreds of dollars. People who deal with real-world data that has a lot of missing data where it's a complicated mechanism may have no choice but to spend $500, $600, $700, $800, $900 on this software because it specifically does these complicated missing value imputation routines. Okay, we're out of time. We'll pick back up there on Monday, and probably most of next week, if not all of it, will be missing data stuff. And you'll get your exam on next Friday, remember. So no class Wednesday or Thursday this week, or Friday this week. Hope you have a good Thanksgiving. Okay. I will probably not have a Q&A tomorrow since we don't have a homework assignment. I'll post something on the discussion board, and if anybody has something you would like me to talk about, I'm happy to do it. But if I don't hear anything on the discussion board, we probably won't have one. Okay, thank you.